All right, let's start. Hi, everyone. Welcome to Student Colloquium. I remind the students who are registered for this course, it's a one-credit course, and part of your work in this course is to understand the talks. So you should ask questions whenever you have them. Don't wait until the end. Interrupt the speaker. It's okay, at least in this colloquium. And the speakers are warned. And the lectures are recorded, and later else those who are registered can get it on Canvas, and the rest guests and speakers will be informed where to watch themselves the talk. All right, without further ado, our speaker today came to us all the way from Moscow in Russia, which is the only good thing about COVID. We can easily travel by Zoom. And Vladlen Timorin will talk about Hopf map. Vladlen, please.
Yeah, thank you so much. I will share the screen. So now hopefully everybody can see. Okay, so I will start with a very elementary introduction, but things will proceed. And if there are any questions, again, please ask. I will start with two stories, somewhat related to Hopf maps, although not very, well, maybe not very closely related, but I would like to present them as a motivation. So let me start with the rational parameterization of the circle. Consider the usual circle in the plane. Say the center of the circle will be in the origin and the radius will be 1. Of course, you all know that the circle can be easily parameterized by trigonometric functions, but it's also useful to use rational functions instead of trigonometric functions to parameterize the same curve. And a rational parameterization, for example, may look as follows. This is, of course, not the only rational parameterization, but probably the standard rational parameterization of the circle. And to see why this parameterization works, you can do several things. One possibility is just to substitute these expressions into the equation of the circle, into the x squared plus y squared equals 1, and verify it. So see that you get the true identity. So this is the true identity you get. And this formula will be important. We will also consider some generalizations of this formula. So of course, this formula is ready in I open the parentheses. And okay, let me skip further comments on this. So there are, of course, other ways of verifying the same thing, that this parameterization works. So alternatively, one way to obtain the rational parameterization from the trigonometric one is to introduce the tangent. It's also written as tan. The tangent of theta over 2 of the half of the angle, and then using the high school trigonometry, you can express both cosine and sine through this tangent and obtain the same expressions. Geometrically, this also has a transparent meaning. The t, which is the tangent of the theta over 2, is this this y coordinate where you fix some point of the circle. In this case, you fix -1, 0 is a point of the circle. And then you consider all lines through this point. Each line in this pencil crosses a circle in some point, and it also crosses the vertical line, the y-axis. So this is the y-axis. And these 2 points will correspond to each other. So in this way, you get a projection, the so-called stereographic projection, from the circle to the line, or the other way around, from the line to the circle. And so every point on the circle, so a blue point here, will correspond to a new point of the line with the value of the y coordinate equal to t, and vice versa, every t will give rise to a blue point of the circle. So this t is the same as the tangent of theta over 2, because this angle is theta. It's the cosine and sine of this angle that parameterized a point of the circle. And then this angle is theta over 2. So t is the tangent of theta over 2. You may know this well, so I will not. So is everything okay? Is it too simple?
I think it's fine.
Okay. So then let me tell you a different story. This story is also very, very classical and rather simple. It's called the Diaphantes Brahmagupta Fibonacci identity, named after 3 distinguished mathematicians of the past who didn't work together, of course, because they lived in different places and different times. Diaphantes lived in 3rd century, Brahmagupta in 7th century, Fibonacci in 13th century. But they all independently came up with the following formula. This is a very simple but a remarkable identity, which is closely related to multiplication of complex numbers, but in principle, you don't need even to use complex numbers to verify this. You can simply open the parentheses and see that the identity holds. So this is a way to represent the product of 2 factors, each of the factors being a sum of 2 squares, again as a sum of 2 squares. So if you take the sum of 2 squares, x1 squared plus y1 squared, and multiply it by another sum of 2 squares, x2 squared plus y2 squared, then of course, after open the parentheses, you can represent this product as a sum of 4 squares. But, and this is a very special phenomenon having to do with the number 2. If you have just 2 squares, then you can combine the terms and represent the result as, again, the sum of 2 squares. This will not be possible for 3 squares. It will also be possible for 4 squares, but this is a different story. So this identity has some number theoretic consequences. For example, if you know that each of 2 numbers, a and b, is representable as a sum of 2 squares, I mean squares of integers, then the product of 2 numbers, a times b, is also representable in the same form as a sum of squares of 2 integers, which is, of course, a very easy consequence of the Diaphantes Brahmagupta Fibonacci identity. This identity is also closely related to multiplication of complex numbers, because you can rewrite the identity as the statement that the modulus of the product of two complex numbers is the product of the moduli. If you take the squares of both sides, then exactly you get the product of sum of squares in the left-hand side and sum of two squares in the right-hand side. Is everything okay so far?
Yeah.
Okay. Then I will go to some generalizations. So some formulas with sum of squares based on what we already seen when parameterizing the circle. So rational parameterization of the circle is based on this formula. The only difference with the formula we had before. So let me show here. So this is the formula we used. And in this formula, we had just one parameter t. And now in the new formula, we have two parameters, u and v. However, the formula is essentially the same. It's the only difference is that this is a homogeneous form. If you divide, both variables, u and v, enter in the fourth degree. So if you divide, say, both sides by u to the fourth, then you get the same expression with t back, where t will be just the ratio of v and u. So the two formulas are essentially equivalent, but it's sometimes better to write the parameterization in this homogeneous form, well, aesthetically as well as mathematically. So we get this parameterization. Now there are two parameters, u and v, rather than only one parameter t. But of course, there is some degree of freedom. Namely, if you multiply both u and v simultaneously by the same factor, then you get the same point of the circle. So it looks like you parameterize a point of the circle. Circle is a one-dimensional curve. And we parameterized this one-dimensional curve with two parameters. However, these two parameters, what matters is only their ratio. So that we can multiply both parameters by the same number and get the same point of the circle. Okay, so the only, well, maybe just one remark here on the usefulness of this homogeneous form. So on the one hand, having two parameters like this is almost the same thing as having one parameter, namely their ratio. On the other hand, it's not exactly the same thing, because sometimes we may have u equal to 0, and then the ratio is not defined. You can formally set it equal to infinity, but it's still, you need to do something. It's not defined as a real number, but the homogeneous formula still makes sense. If u is equal to 0 and v is not equal to 0, then everything is fine with the homogeneous formula, and something needs to be added for inhomogeneous formula. So now I want to use a similar formula for complex numbers. So far u and v were reals, and now I want to use this formula for complex numbers, which holds for the same reason. It's very easy to verify this formula by opening the parentheses, and the only non-trivial thing, the only non-trivial identity we have to use here, a part of high school algebra, is this Diaphantes brahmagupta Fibonacci identity. So if we use it here, then in the same way we verify this. And of course, for the sake of this formula, it doesn't matter here. W bar denotes the complex conjugate number, but the formula will still be true if instead of W bar, I put W here. It will be just nicer with W bar later. We'll see it later. Okay. So now I repeated the same formula. And what this formula gives us is a parameterization of the sphere, of the two-dimensional sphere in this three space. So let me draw a picture. So now imagine a three space with coordinates psi, eta, and zeta, and a sphere in this three space given by the equation the sum of squares of all coordinates equals 1. Then very much similar to how we parameterized to how we parameterized a circle, we can parameterize this sphere in a homogeneous form by setting the coordinates psi and eta to be the real and imaginary parts of this expression, and the real coordinate zeta as this is a real number. So then we just need to verify that what we get by using these formulas is a point of the sphere. So we need to verify that psi squared plus eta squared plus zeta squared is equal to 1. And this is immediate from the formula we already had. Because after we multiply by the common denominator, we get exactly the same formula. So what we get is that a point of the sphere is represented by two complex parameters. This is a somewhat excessive parameterization because two complex parameters, they're equivalent to 4 real parameters, and the sphere is only two-dimensional. So we have 4 parameters to parameterize a two-dimensional object, and this is too much. Of course, some parameters are excessive, and it's easy to see that the formulas look so that we can multiply z and w simultaneously by the same non-zero complex number and get the same point of the sphere. This is how to get rid of two parameters. We have a freedom of multiplying z and w by the same complex number, and one complex number is means two real numbers. Okay, so if we now restrict to just 3 real parameters, so if we say let s and t be the real and the imaginary parts of z, u be the real part of w, and the imaginary part of w will be just 1. So we fix one of the 4 parameters. Then we obtain a map from the 3 space with coordinates s, t, u to a two-dimensional sphere. What we do is just we substitute it to z and w, and z and w will then depend on 3 parameters, and therefore through the formulas we already have here, c, eta, and zeta, namely the point of the sphere, will also depend on these 3 parameters. So in this way we get a map from R3 S2, where R3 is the usual three-dimensional space, and I'm sorry, S2. And S2 is the sphere in the three-dimensional space. As a sphere, it's two-dimensional. This is one version of the Hopf map. Hopf map was, well, this version and some other version of Hopf maps were invented by Heinz Hopf, who was motivated by topological problems. But I would like to concentrate on algebraic and geometric aspects of Hopf maps, although I will also mention this topological, the main topological property. Okay, so an equivalent description of the same map will be as follows. So this description is even easier in terms of formulas. If we have two complex coordinates z and w, then what we need to take is just to take z over w, take the ratio of the two complex numbers, and get a point of the plane. So this will be a point. This will be just a complex number, which can be represented as a point of the plane. Well, to be honest, it's not just a complex plane. We also need to add one point to this complex plane because the denominator may turn out to be 0, and then the ratio should be set to be infinity. So it's the so-called extended complex plane. And then a stereographic projection will give a correspondence between this plane of complex numbers, the extended plane of complex numbers, and the two sphere. So this is an alternative description of the same map, and it's easier in terms of formulas. Moreover, it's you can see that everything depends on the ratio, which was a kind of implicit in the previous description. We, of course, observed that if we multiply z and w by the same complex numbers, then we get the same result. Therefore, things should depend just on the ratio, but somehow that wasn't very explicit here. And here we see that this is just the ratio plus the stereographic projection. I will comment on stereographic projection on the next slide. But let me state an important property and interesting, in my view, property of this Hopf map. And the property is that this map from the 3 space to the 2 sphere takes all straight lines to circles. In the 3 space, we have plenty of straight lines. And on the sphere, we have circles, namely a circle on the sphere is by definition just the intersection of the sphere with any plane. Any plane cuts a circle from a sphere. And the theorem is that Hopf map takes any line whatsoever to some circle. Now, let me recall what the stereographic projection is. A stereographic projection is a central projection from a point on a sphere to some specifically chosen plane. Namely, we can arrange so that the point from which we project is the north pole of the sphere. And then we project onto the plane that is tangent to the sphere at the south pole. This will be a plane parallel to the plane tangent to the sphere at the north pole, but actually we can choose any plane parallel to that, but not passing through the north pole. In particular, we can take the plane tangent to the sphere at the south pole, or we can take, say, a plane parallel to this and passing through the center of the sphere. And then every array emanating from the north pole will intersect a sphere at some point, and it will intersect the plane at some point. So the point of intersection with the sphere corresponds to the point of intersection with the plane, and this correspondence is called a stereographic projection. So in this way, every point of the sphere, except for the North Pole, has its image in the plane, and every point of the plane has its image in the sphere. Now, if we add the infinity to the plane, then this correspondence will be one-to-one, because the North Pole will then correspond to the point at infinity. And an important property of the stereographic projection is that it takes all circles in the sphere to circles or lines in the plane. So these are some other pictures on stereographic projection. You can think of a bulb given some light at the North Pole, and then what you see as a shadow in the plane will be the stereographic projection. Any questions? Okay, so probably the main property of the stereographic projection is that it takes circles to the so-called generalized circles. So circles in the sphere are mapped to generalized circles in the plane. Generalized circles are just circles or lines, where lines are regarded as limit cases of circles. So if we say fix a point and a tangent line at this point and make the circle pass through this point tangent to this line, and let the radius of the circle go to infinity, then in the limit, the circle will tend to the tangent line. So the tangent line can be thought of as a limit of a family of circles. And thus it's natural to unite circles and lines and call them generalized circles. And these are, alternatively, these are images of circles under the stereographic projection. So this can be seen as lines if and only if, so generalized circles passing through infinity are lines. And if they, so if a generalized if a generalized circle passes through infinity, then this is a line, and if it doesn't pass through infinity, then this is a genuine circle. So a very classical theorem of Möbius says that if we have a bijection of, well, just enough to require that f is a bijection, we don't even need continuity. We don't even need to assume continuity here. So if we have a bijection from the extended complex plane, extended plane of complex numbers to itself, that takes generalized circles to generalized circles, then necessarily this bijection is either fractional linear like this, or the composition of the complex conjugation and the fractional linear map. So now a theorem equivalent to the property of Hopf fibration of Hopf maps already stated is the following. So the map from the 3 space to the extended plane of complex numbers given just by taking well, putting the first 2 numbers in the numerator and third number in the denominator plus I. So this map takes lines to generalized circles. Well, in principle, this can be verified by direct computation, but I will sketch a more conceptual proof if I have time. Is everything okay?
Yeah.
Okay.
Yeah,
So
you're still coming through.
Mm-hmm.
No, I was just saying you're still coming through clearly.
Okay. Thank you. So now let me briefly discuss a different version of a Hopf map. The versions are closely related, but these are not exactly the same map. So let us now put 4 real parameters and arrange them in form of 2 complex numbers. So x0 and x1 will give rise to the complex number z, and x2 and x3 will give rise to a complex number w. And then, well, the same formula as before. So these formulas, the same formulas give a map from the three-dimensional sphere, which is the sphere in the four-dimensional space, given by the similar formula, the sum of squares of all coordinates is equal to 1. So this three-dimensional sphere is mapped to the two-dimensional sphere. The formula is the same. The difference is, however, that before we restricted to some three-dimensional plane. So before we set this coordinate to be equal to 1, and now we use all four coordinates and restrict it to the sphere rather than to a hyperplane. So previously what we had is this kind of restriction, x3 is equal to 1, and now we use a different kind of restriction. We use this equation x0 squared plus x1 squared plus x2 squared plus x3 squared is equal to 1. So we restrict to the sphere. And this is also a version of the Hopf map. And in this case, this is a map from the three sphere to the two sphere. This was the map interesting from the point of view of topology, and I will try to explain why this is so interesting. But before I say that, I will need to explain how to think of this, how to visualize this in terms of pictures. So it may seem hard to visualize the three sphere, because this is an object in the four-dimensional space, and it's hard to imagine four-dimensional space. On the other hand, the things are not so hard, because similarly to representing a two-dimensional sphere as just a plane plus a single point at infinity, this we can do by means of a stereographic projection. So similarly to this, we can think of the three-dimensional sphere as just the usual free space plus a single point at infinity. So you can try to imagine that the sphere contains the free space in which we live. And the only difference is that if you go, well, if you go in every direction sufficiently far, then you come back from the opposite direction to the same point. So in fact, living in the three space, we don't even know whether we live in the three space or in the sphere. Therefore, all pictures in the three sphere can also be drawn in the three space, and this I will be using. Is this okay?
Can you go over why you can use them for both again?
Using what? I'm sorry.
You said the three sphere.
Mm-hmm.
I can't tell. Can you go over? You said you can use that instead or you can use it as well. I didn't catch why you can use it for both. Fortunately, I don't quite have the terminology down.
Yeah. So I'm saying that in order to draw some picture, in order to draw some figure in S3 in the three sphere, you can draw a picture in just the three space, because, well, similarly to let me write here. So let me first start with the two sphere. So the two sphere can be mapped or represented by, so I put the equality sign, but I don't mean that these two things are equal. I just mean that you can use one thing instead of the other. So the two sphere can be represented as the two-dimensional plane plus one point at infinity. Is this clear enough?
Yeah, that makes more sense. So they're not equal. You can just substitute them, is what you're saying.
Yes.
Okay.
I mean, for example, if you want to draw some figure on the two sphere, you can use instead a plane. Draw this figure in the plane, so whatever you want to draw, and then stereographically project it to the sphere.
Okay, that makes sense. Thank you.
Right, and then I suggest to do the same thing with the three sphere, because here, the difference of, what happens when we add one point at infinity. So in small part of the plane, nothing happens. But if you go, say, in any direction sufficiently far, then imagine that the corresponding point of the sphere can pass through the North Pole, and therefore it can get back like that. And similarly with the three sphere and the three space. So you can think of the three sphere as the three space plus one point at infinity with the same convention. If you go in every direction, then you eventually may get back from the opposite direction. Okay. So the pictures I show here are in the three space, but they correspond to pictures in the three sphere by means of the high dimensional version of stereographic projection. And in these terms, I can now explain the structure of the Hopf map. Namely, it's interesting to look at point preimages. This is a map. Again, the Hopf map is the map from the three-dimensional object to a two-dimensional object. Therefore, we'll lose one dimension, and it would be natural that preimages of points are one-dimensional curves. Indeed, if you take the preimage of any point, then, and this is a very straightforward computation, you can compute that the point preimages, these are also called fibers, the fibers of the Hopf map are circles. They are circles in the three sphere, but they also represented by circles in the three space, because the stereographic projection takes circles to circles. So first of all, any fiber is a circle. Since the entire three sphere, in particular the entire three space, is mapped to the two sphere, you can think that the entire three space is fibered by circles. That is, it's represented as a disjoint union of different fibers, each fiber being a circle. So each point of the three space is a point of some distinguished circle. And there is a way of visualizing this. So there are many circles that are all disjoint and whose union is the three space. And these circles are fibers of the Hopf map. They also form what is called the Hopf fibration. The Hopf fibration is this way of representing the three sphere as a union of circles. How the circles are arranged? They are so this figures show how the circles are arranged. So first of all, they span certain tori. Let's take one line. One line will be the z-axis, and this is a line passing through the point at infinity. So you should think of this line as again a circle, because even though it's not a circle, it's a line, but it's the image of some circle under the stereographic projection. It's just that this image passes through infinity. All other circles will be genuine circles. So this will be one of the fibers. One of the fibers will be just vertical line. All other fibers will be arranged into tori. And this tori will share the same axis, namely the z-axis will be the axis of all these tori. So a single torus is shown here, and this figure is more complicated. It shows parts of several tori, coaxial tori, and each of the torus contains a family of circles. Okay, each of these tori contains a family of circles. So here you also see several pieces of several tori, and how to understand this picture. So here you see the image in the two sphere, and you see some several curves of which we take pre-images. Say we take three families of points here. One family encompasses these points, and well, this arc, then this arc, and this arc, the three arcs. And then for each point of the three arcs, you take the corresponding fiber and draw it here in the three sphere. So this is the corresponding picture in the three sphere and the three space. All these fibers are circles arranged into tori, and it's also remarkable that any two of the circles are of course disjoint. They don't intersect in the free space because they are fibers of some map. Fibers cannot intersect, obviously. But it's interesting that any pair of such circles is linked. They're like this. So you have two circles that do not cross, but that cannot be pulled apart without a crossing. So it's like in a keyring. So this is, by the way, one of the physical model which models the same topological arrangement of circles as in the Hopf vibration. So any two circles are linked. Are there any questions? Okay. So let me now explain how we get these circles. Given a torus, we can construct several families of circles on the torus. One interesting way of drawing circles on the surface of a torus is due to Velar, a French mathematician and engineer. What you do is you cut a torus by a plane that is tangent to the torus at 2 points, 1 point here, and you can see that this is a point of the tangency because the intersection of the surface with the plane looks singular. So it doesn't look like a piece of a line, it rather looks like two intersecting lines, and that means that here you have the tangency. If you don't have a tangency, then the intersection looks simpler. It looks like a single line, a piece of a single line. So if you cut a torus like that, then in the cutting plane, as the intersection, you get a pair of circles. So you can easily verify that this is a pair of circles. So here you can see them better. So a pair of circles. And these are called Velar circles. So you see that any plane cuts two Velar circles out of a torus. And therefore, there are two families of Velar circles on the torus. So that circles of the same family are disjoint and linked. And circles of different families intersect. So when you cross a torus by a plane like this, you get two circles of different families. And in general, if you take a torus, then there are four circles through each point. Because if you take any point of a torus, then you can draw a parallel, which is a circle, a meridian, which is also a circle, and two Velar circles, so that through every point of the torus you can draw four circles, and this is a rather special geometric property of the torus. It's not very common that you can draw four circles through every point of a surface. There is even a classification of such surfaces where it's possible. And these arrangements of circles are used in art and architecture, for example. So this figure shows some fragment with Velar circles. So these are interesting properties of the Hopf maps. And well, maybe if you have some questions, I may answer questions, and then just to give one single proof in my talk, I will give one proof if I still have time. Are there questions?
I have a question. Is it Strasbourg, the cathedral?
I believe so, yes.
Okay.
Okay, so the statement I want to prove is that the first version of the Hopf map, that was, let me scroll there. So that was a map from R3 with coordinates S, T, and U to the two-sphere. The statement about this map is that it takes any line to a circle. And I want to prove this statement and to give a rather conceptual proof using a little bit of linear algebra. So I will need a lemma, which says the following. Let's consider a curve given by the following parametric equations. Each of the three coordinates is represented as the ratio of two quadratic polynomials in one variable. So that we have four quadratic polynomials of one variable tau, and then we form three ratios, and this will give a curve. So the statement about this curve is that this curve is a plane curve in the sense that it belongs to some plane. It lies in some two-dimensional plane. Is the statement clear? Okay, now the proof. Let's consider the following equation. I just write a linear combination of the four quadratic polynomials. And this will be an equation on the coefficients of this linear combination, namely the unknowns will be lambda naught, lambda 1, lambda 2, and lambda 3. And the equation should be, the equality should be identical with respect to tau, in the sense that, well, we have just a quadratic polynomial. So in order, well, when we say that a quadratic polynomial vanishes identically, that's equivalent to saying that all coefficients of this quadratic polynomial vanish. And then a quadratic polynomial has 3 coefficients. So that what we have here is a system of 3 linear equations on 4 unknowns. So we have 3 coefficients that must be equal to 0, and we have 4 unknowns, namely the lambdas. Okay, so since we have a linear system, and it's important to say that this is a linear system where the number of unknowns is bigger than the number of equations, then we know that there is a non-trivial solution, a solution in which not all the lambdas are 0. Take this non-trivial solution and form an equation. This will be an equation of some plane in the 3 space. And then it's easy to see that our curve lies in this plane because, well, you multiply by the denominator and you will see that the curve lies in this plane. So we found a plane in which the curve lies, therefore we proved the lemma. Is everything okay with the lemma? Okay, then it remains just a little bit to prove the theorem, to deduce it from the lemma. What we need to observe is when we take a line and map it by means of a Hopf map, well, like that. So if we take a line, that means that S, T, and U will be linear functions of one parameter tau. And we have to substitute these 3 linear functions into the equations for the Hopf map. And we don't even need to know the details. The only thing we need to see here is that these are fractional quadratic expressions, that the numerator and denominator are quadratic polynomials. When we substitute linear polynomials into these quadratic polynomials, we get, again, fractional quadratic expressions. Namely, if we take the line and map it by the Hopf map, we will see a curve like this. So this will be a curve like this. This will be given by 4 quadratic polynomials. And we know that this is a plane curve. On the other hand, we know that this plane curve lies in the sphere because the Hopf map is a map to the 2 sphere. A plane curve that lies in the sphere is a circle or a part of the circle. So that we proved that every line gets mapped to a circle. Okay, so this was the only proof and the end of my talk. So I took images from some open sources, and I will be happy to answer questions.
Okay, any questions, please? So for the benefit of everyone, so there are other Hopf maps, as you mentioned. So for example, 7-sphere to 4-sphere, right?
Yes.
Does it have interesting geometry of the same kind?
Yes. So I will not comment on topological properties, but just to state an analog of the geometric property, well, you can also say that the Hopf map from from S7 to S4 takes all lines to circles in the following sense. So instead of lines, you take great circles in S4 and in S7. So geodesics in the sense of the usual metric, and every great circle in S7 is mapped to a circle in S4.
But
And
not a great circle, some circle.
Not necessarily a great circle, just some circle, as in the case of usual Hopf map.
Okay, thank you. More questions? Okay, if there are no questions, Len, thank you very much. And I will send you the link to recording once I receive it from Zoom. And I hope to see you in person someday. Hopefully by the summer it will start to go away slowly. All right, good night. It's night in Moscow.
Thank
Sorry
you.
for making you work. Good night.
Yeah,
Goodbye.
thank you.
Thank you.
Bye.
Thank you.